Oh my god, I am very, very sorry for starting very late. I had some things to do, but let's see. Anyways, good evening, everyone. Welcome back to our daily studies. Sorry, I'm starting late because I got busy with something else, and yeah, but I'm here now, and it's good to be back. So today I'm going to cover something new. Um, I've been meaning to study this data structure for a while now. So let me just jump on it today. I'll use today's opportunity to show you how I study on a normal day when I'm studying something new. Sorry. So I'll just quickly. Hold on. So I have some. Uh, okay, can you hear me now? Can you hear me now? Sorry, I. Yeah, good evening. Good evening. Welcome. Um, so we're going to study something together today. I've not really done trees before, so I'll just take you through, the way I study, the steps I take to, try and learn something new. So, which is what I'm going to do today. I would have revised a question before I start studying something new, but I think because I started late, right, I'll just go ahead and learn about binary trees first, and uh then we can you know revise a question or two. So yes, the notification worked. Okay, that's very nice. So let's see. So I want to learn about binary trees. Binary trees are something they are, I would say, very fascinating, but I've been seeing drawings like this for a while, and I wondered what really it was about, right? So let's find out what it is. I'll leave the links in the description. Let me quickly edit the description links below so that you guys also have access to what I'm using to learn. And let's save this. Okay, so I've posted the link in the description. So I will take you through my learning process today. It's funny. I usually learn these things before I stream, but today I just decided to, you know, learn while I'm streaming. So let's see. Um, Binary trees. So a binary tree data structure is a hierarchical data structure in which each node has at most two children, referred to as the left and right child. Okay. It is commonly used in computer science for efficient storage and retrieval of data with various operations such as insertion, deletion, and traversal. Hmm. That's not a lot of. Okay, so let's see. Um, I'll go back to this part. So this introduction to binary trees. This website is really good for studying. So um, yes, yeah. So binary trees. Let's take a look. So binary tree is a non-linear data structure where each node has at most two children. In this article, we'll cover all the basics of binary trees operation. Binary trees, I don't know, binary tree, not trees. I mean, okay. Binary tree operation and what else? Its implementation, advantages and disadvantages, which will help you solve all problems based on binary tree. So, what is binary tree? Okay, so we are here. So we have at if you go to this page, right? You can click on this link to get to this page here that I'm currently reading. So, uh, this is what I'm studying currently. So you can have access to it as well. Um, okay, so binary tree is a tree data structure non-linear in which each node can have at most two children where which are referred to as left child and right child. The topmost node in a binary tree is called the root, and the bottommost node are called leaves. Hmm. Okay. A binary tree can be visualized as a hierarchical structure with the root at the top and the leaves at the bottom. Okay, that's really nice. Don't worry, you get to understand. Once I understand and explain it to you as well. So just hang in tight. All right. So let me bring back my screen. I think when I bring back this screen here, the chat goes off. So I will be responding to the chat until I'm done reading again. All right. Let's see. So I've read this part. So here's a representation of a binary tree. So far we know a binary tree has certain parts. I'll just remove this here. That's something I did yesterday. So let's take a few notes. We know there will be so binary tree, right? This has a root, leaves, right? And child. So there is a child node. Okay, so the leaves are basically the child nodes. Leaves will be the child, and each child has at most two other nodes, right? So they will have a left child, a left child, and right child. Don't worry, this is nothing. I'm just trying to write down the things I've read. So let's carry on with the next step. So we have each node in a binary tree has three parts. It has a data, a pointer to the left child, and a pointer to the right child. Okay. So here's an image. We have the root node. I'll bring this image here to see, what's going on. Let's increase this a bit. So you can see we have the root node. The root node. So here is something interesting about this. So this part here, right, are the nodes that will point to the left and right child. So each child node has a left and right, as you can see here. So we have the left child here. This is the left child of this node here, and this is the right child of this node here, right? And this node, this left node, also has its own left child, right, which is this node here. and its right child is also this node. Okay. So yeah. Then what else? What else? So this is the root node, the node at the top, right? The topmost node is the root node. I'm not sure if this is. I mean, I'm kind of. It's beginning. It's looking like what do you call that data structure? Linked list, right? With linked list, we also have a topmost node that is also known as the head node, and in this case, we have root node. And I'll say this looks more like a doubly linked list, but let's just continue and see where it takes us. So below is the representation of a node. So let me of a binary tree. So we have the three parts of the node. We have the left, the right, and the value, right? So uh, this this would have been our value, right? Value. This is the left node, obviously. This is the right node as well. Okay, that's good. That's good. Okay. So let's see. The node in a binary tree is this, right? So this is how it creates the node. And we also know we've done something similar to this with linked lists. In short, you know what? This here, right? This value is the key. So when you create an instance of this node, I don't know if this is going to be the value. I don't know why they are calling it a key here, but I'm sure this is the value you pass into the node. Sorry. Binary tree can be classified into multiple types based on multiple factors. So we have multiple types of binary trees. I don't even know one yet. Anyways, let's go. So we have a full binary tree. I'll open this here. A degenerate binary tree, and a skewed binary tree. So this is on basis of the number of children, right? And then on the basis of completion levels, we have a complete binary tree, perfect binary tree, and balanced binary tree. Okay, and then we have on the basis of node values, we have a binary search tree, and AVL tree, a red black tree, sorry, a red black tree, B tree, B plus tree, segment tree. Wow. Um, let's see this part. What's a full binary tree? Uh, a binary tree is a tree data structure with a maximum of two children per node. Okay. Um, yeah. So that's the left and right child nodes. We commonly refer to them as the left and right child, as each element in the binary tree may only have may only have two children. Sorry. So what is a full binary tree? A full binary tree is a binary tree with either zero or two child nodes for each node. So here is a full binary tree. This is our root node. Our root node has two child nodes, and this other node too has also two child nodes. So it's either going to have zero, right? The reason why this is balanced is because it doesn't have any child nodes. So this is good. Um, let's see. So full binary tree, let T be the non-empty full binary tree. Then if T has, I don't know if this L or I internal node, the number of leaves is equal to I plus 1. The number of leaves L is equal to I plus 1. Okay. See, I'm wondering about, but let me just keep going. I think there should be a part where we see a basic implementation of a binary tree. Okay, here. So here's what we have. Um, Before I get to that, so we can see there are other operations of binary tree. We will take a look at insertion in a binary tree. We can insert a node anywhere in a binary tree by inserting the node as the left or right child of any node, or by making the node as root of the tree, right? So we can insert a node anywhere in the tree by making it the left or right child of that particular of any node, any existing node in the tree. And then we can also set it as the root node of the tree, right? Okay. Algorithm to insert a node in a binary tree. I think this is going to be O of n, because we have to traverse a couple of nodes to insert the node, right? But anyway, let's see. Check if there is a node in the binary tree which has missing left child. If such node exists, then insert the new node as the left child. Check if there is a node in the binary tree, and also for the right child, you insert it as the right child. If we don't find any node of the if we don't find any node with missing left or right child, then find the node which has both the children missing and insert the node as its left or right child. Okay, that makes sense. That makes sense. So let me quickly bring this back. Um, Sorry, my phone just rang. I did not want to pick this call. Give me a minute. Okay. All right. So, um, here's what we've been told. So there are some illustrations here to help us understand what it is. So here we have a binary tree, right? All the nodes are balanced in this tree. So if we want to insert 4, we have to choose this node here without a child, right? And then insert 4 as its uh, left or right child. Yes. Okay. Otherwise, when there are nodes in the tree, we can check if that node has a left child or has a left child with a missing right child. Then we insert our new node as the right child. Otherwise, we'll make our new node the left child if it already has a right child. Sorry, let me borrow a minute quickly. All right, sorry for the inconvenience. Um, okay, so let's read the next part. So we have traversal of nodes in a binary tree, right? Traversal of binary tree. Okay. Basically we are traversing every node in the binary tree. So let's see how the traversal is done. So traversal of binary tree involves visiting all nodes of the binary tree, Okay. Tree traversal algorithm can be classified broadly into two categories. We have a depth first search and a breadth first search. Finally, I'm learning about this thing, DFS and BFS. Okay, so let's see what DFS is. Ah, oh, today is not a good day. Today is not a good day, but we shall make today a good day. So, let's take a look at this other part. Oh God, I'm so sorry. Um, anyways, let's continue with what we have here. So we can pre-order traversal, current left to current right. So I was talking about DFS and BFS, right? DFS, BFS. So pre-order traversal, current left, right. So visit the current node before visiting any node inside the left or right subtrees. Oh, what does that mean? Visit the current node before visiting any nodes inside the left or right subtrees. Here, the traversal is root, left child, and right child. Okay, so we go roots from roots. Let me see. So we have root, left child, and left child to right child. So we start from here, from the root. This is the root node here. Then we go from here to here, right? Left child, then right child, before visiting any other node. Let me close this part here. Okay. So it means that the root node is traversed first. Oh, so there is in order traversal. Left, current, right. So visit the current node after visiting all nodes inside the left subtree before visiting any node within the right subtree. Here the traversal is left child, root, right child, left child, root, right child. It means that the left child is traversed first, then its root node, and finally the right child. What does this mean? It means that the left child is traversed first, then its root node. I, you know what? There has to be, let's see. So this is depth first search. Okay. So depth first search has three parts: pre-order traversal, in-order traversal. Visit the current node after visiting all node inside the left subtree, but before visiting any node within the right subtree. Okay, so if we visit, do we have to visit all the node in the left subtree before coming back to the right node of this root? I'm not sure, but let's see. I'm still thinking. Okay, this it means that the left child is traversed first. Yes, then its root node, and finally the right child. Post order traversal, I think it should be the opposite of this, or left to right current. Okay, so visit the current node after visiting all the nodes of the left. Well, what are they referring to as current node? Right. So visit all the nodes of the left and right subtrees. Visit the current node after visiting. So here the traversal is left child, right child, and then root. I'm not sure what I'm reading actually makes sense. Uh, but that's how it is, right? When you're learning something for the first time, it's confusing. But anyways, that's why we are here. So so here we have breadth first search. So visit nodes level by level and left to right fashion at the same level. Okay, so we in this case we visit every node here and every node here because these two nodes here are the same level, right? So we do that. Um, so it means at the most it means that the most left child has traversed first, and then the other children of the same level from the right to have traversed. Um, Delivery. Yeah, really. They should collect it. Yes. So deletion in binary tree. We can delete any node in the binary tree and rearrange the node after deletion to again form a valid binary tree. So here is an algorithm to delete the binary tree. So starting from the root, find the deepest and rightmost node in the binary tree and the node which we want to delete. Uh, I'm just being, you know, let me check the chat. This is loading, 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 loading. Hello, Code Lifey. Um, I know, right? Yeah. I mean, I usually, study, try and understand something before I stream. But today I started the stream late because I was busy, which means I had not even learned about binary trees before the stream. So this would have been one of those videos where I stream and just you guys just watch me study. But I just want some interaction, right? So yeah, let's see. I'll just go through some really basic step. So we have searching as well. But let's look at a code for binary trees. Oh my god, they are using a deck. I'm sure you guys remember what a deck is. A deck is something we used in um, queues. So let's see implementation of a binary tree. So here is a code for insertion, deletion, and traversal of a binary tree. I really want to know this part only for now. I don't want to learn any more. Um, okay, so let's take a look at this part. First of all, we create a node class, right? This node only has data left. Okay, so left and right are there. Okay, this is good. So insert, insert to insert if root is done. I mean, what's going on here? I thought they were going to create the class for the trees, right? Anyways, but if the root is none, add the new node. This is similar to what is done in linked list. Uh, so queue traverse to queue, blah blah blah. Um, hmm. You know what? Let's bring the code editor here, and I'll try something new. Let's create a folder for binary trees. Binary dash trees. Okay. So I will just put here the basics. Basics here. Okay. So first of all, we need a node. I'll create a class here called node. This node will have. Come on. Our node will have three properties, right? Let's create a constructor function. So this will be neat. We'll need a value, so I'll just put a value here. We'll say self dot what are the we have a value which is going to be equal to this value here, and we have the left and right child, right? Self the left child. Oh, let's just put it like this. You know what? Let me just call it left and right. This will be none at first, and self dot right will be done as well. I mean, we can assign these two to none together, but you know what? This is still fine. So let's see. So insertion, right? Insertion is basically similar to what we do um in linked lists. So we first check if the root is none, right? And if root is none, then we set a new instance of a node to the root, right? Otherwise, we traverse the root. So here is where it has become interesting. Why is the root being appended to a deck? That is something I don't understand. Let me take a look at other implementations of a binary tree to really verify, if this is actually true. So let's see. Um, hmm. So binary tree is a type of data such a yeah BFS. So binary search tree. So this restriction that the node have maximum of two chars. You know what? Anything I read, I'll just put it in the description. So uh okay. So anything I read, I'll put it here. I'll save. Okay, so the algorithm like traversing search insertion, deletion become easier to understand, to implement, and to run faster. Interesting. Uh oh, there is normal trees. Really? Let's see. What's this one? Wait, I must have skipped something, right? I must have skipped something. Let's read this part here. I'll put this here. No, 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 no. Jesus. Let me see. Okay, so what are you missing? Clients don't give a damn. um, yeah, I just have a little bit of interruption happening in the house right now, so I needed to go and sort out some things quickly. Um, yeah, hopefully I don't leave again, but let's continue. So I've been providing all these links in the description so you can read them and um, also follow along. So here we have a tree data structure. Let me increase this. I think it will be better for us to see. I can't collapse the sidebar. This is so annoying. Ah, so trees are similar to linked lists, right? In that each node contains data and can be linked to other node. Yeah, so that's quite a similar characteristics. We have previously covered data structure like arrays. Okay, this is not what I want to read. However, trees are different. In a tree, a single element can have multiple next elements, allowing the data structure to branch out in various directions. Okay, the data structure is called a tree because it looks like a tree. So here are some basic stuff you know, let's see. I wanted to see an implementation of a tree, but you know what? This is still good to read, right? So some visualization. So this is the whole tree. This is the roots. Okay, the lines are called edges. Okay, these are the nodes. Okay, the leaf nodes are nodes connected to other nodes. Wait, leaf nodes do not have child nodes, right? So when a node is without a child node, then it's called a leaf node. Because here A and C are grayed out, which means they are not leaf nodes. So they are, I don't know, nodes, normal nodes or parent nodes. Anyways, so we have child nodes, parent node. Yes, okay, parent node. And height, tree height is what? Tree height is 2. Okay. So from the root to the last child node of the parent node. Okay, that's how we determine the height of the tree. The size of the tree, what is the size? The size is every single node in the tree. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Uh, so here are some nodes. The first node in the tree is called the root. I've read that already. Uh, a node can have 0, 1, or many child nodes. That's true. A node can only have one parent node. Of course, this node here has one parent. Let's see. Leaf node. Each leaf node here have a parent. Even this child node here has its own parent. The parent of this node A here is R. So okay, okay. So we have types of trees. Trees are fundamental data structure in computer science. So represent a hierarchical relationship. These tutorial covers several types of trees. So we have binary trees. Each node has up to two children. The left node has the left node and the right node. Sorry. So those are the two children in the binary tree. This structure is the foundation of for more complex trees types like binary search trees and AVL trees. What are AVL trees? What's the meaning of AVL? AVL trees. Oh, so it's not even an abbreviation. That's just the name. AVL trees. Well, a type of binary search tree that self balances every node so that for every node the difference in height between the left and right subtrees is at most 1. Okay. So balance is maintained through rotation. This is not what I'm interested in. Well, it's kind of good to know this, but at this point I just want to know about the binary. So let's see what we have here. Can bring this up. Let me see. Chart. This is really funny, but okay. Let's keep going. It's almost the same information, right? Seeing them, but I want to look at a code and implementation of the binary trees. So we have here, here's our root. So binary trees will be the first tree we learn in the trees data structure. So okay, there's no order tree before binary trees. So pre-order traversal. I think pre-order traversal is breadth first search, right? Oh, sorry. Yeah, BFS. Is it BFS or DFS? Oh, okay. Let's see. Let's see. Yeah. Okay, so it's DFS. Pre-order traversal. Okay, DFS. 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 So binary trees. A binary tree is a type of tree data structure. Okay, I've read this. I've read this. So we have the root node, A's left child, A's right child, subtree. These are subtree. The tree size here will be how many lines, right? So this will be 1, 2, 3, 4, 5, 6, 7. Hmm. Why is it 8? 1, 2, 3, 4, 5, 6, 7. I thought it was 7. No, the tree size is how many nodes are in the tree. Okay, okay. So tree size is the number of nodes in the tree. Tree size is the number of nodes in the tree. The tree height is the longest connection, right? So we have 1, 2, 3. Okay, okay. So hmm. So every a parent node, I logically, right, to be a parent, you have to have a child. So for us to know if a node is a parent node, the parent has to have one or two children nodes, right? So which is what this line says here. Now we have the left child node. The left child node can also be a parent node, but it is a child of another node, right? So left child node is the child node to the left. Right child node is the child node to the right. The tree height is the maximum number of edges from the root node to a leaf node. The maximum number of edges. Edges are these lines, right? I think there was. So here we can see the edges are the lines. So the maximum. Um, hold on. Where am I? The maximum number of the root node to a leaf, of the root node to a particular leaf. So the maximum number of edges, right, will determine the height of the tree. So binary trees versus arrays versus LinkedIn. Um, Benefits of binary trees over arrays and linked lists. So arrays are fast when you want to access an element directly, like element number 700 in an array of 1000. So you can use the insert to get the element. But inserting, deleting elements require other elements to shift in memory to make place for the new element or to take the deleted element's place, and this is time consuming. Yes, insertion and deletion in arrays. Yes, insertion in arrays are very time consuming, especially when you are inserting not at the end or the beginning, right? But insertion within the array will take end time complexity. So I'm not saying it is very time consuming, but it is actually um a certain amount of items in the array, right? Before you insert it at a new position. And deletion is also the same. When you delete an array, when you delete an item from an array, every item in the array has to rearrange, right? So, yeah, binary trees such as binary search trees, AVL. Okay, so linked list, sorry. With linked lists are fast when inserting or deleting. Are they though? Inserting is not fast in linked lists. I don't think so. Because you have to traverse nodes in a linked list uh to insert an item at the end of the linked list. Even within the linked list, right? With let's say you want to insert to a node between two nodes, you have to travel from the head node all the way to the point where you want to insert the new item, right? To insert that item in the node. So I'm not sure this is um this is right. No memory shifting needed. You can say linked list. I think linked list even hmm well, it depends on what they mean by fast. But to access an element inside the list, right, the list must be traversed, and that takes time. Yes, so I mean, if we have 5 nodes, right, I'm not sure, I might be wrong, but I don't entirely agree with the fact that deletion of a node uh, in the linked list or let's say insertion of a node into a linked list is, similar to, is slower, right? Or did you say slow or faster? Let me see. So linked lists are fast when inserting or deleting nodes. I don't think so. Insertion into a linked list will still take O of n time, right? So let's say we want to insert, um let's create a node here. I'll call this node. So here's a node, 1, 2, 3, 4, right? So let's say we want to insert, a 5 here between 2 and 3. We need to traverse this node. We need to start from here because we don't really know where 5 is in memory, right? This is a linked list. Um there is no index assigned to any of these values here, right? They are just the next node in a list connected to a previous node with the next pointer of that node, right? So for us to insert, let's say, you know what, let me put this as 4 and then 5, right? For us to insert 3 between this this node here, right, from 4 to 2 here, for us to insert it, we have to traverse the node from this point all the way to this point before changing the next pointer of this node to our new node, and then our new node will point to the remaining node. So here's what we need to do. We take this, right, we come here, then our new node will be here. So the next of this node here becomes our new node, which is 3, and then the next of this node becomes the remaining node here, right, which is going to be 4 and 5. So insertion is still, O of n, right? Let me just quickly verify that. Time, complexity, inserting a node is not in the middle in the linked list. Yeah, you can see it takes O of n time. O of n does not necessarily mean fast, right? It simply means if there are 1,000 nodes for us to travel to before inserting a node at the 1001th position, we'll still travel 1000 times, right? We'll still iterate 1000 times until we get to the point where we want to insert that node. So I don't think O of n really means fast. Certainly, O of n is actually faster than um, other time complexity like the quadratic time, O of n squared, O n log n, all of those ones. But maybe the context in which they are talking about the insertion here is probably different to what I'm thinking. So it doesn't necessarily mean it's fast. So there's a binary trees, which is, so we have different types of binary trees. AVL trees are great compared to arrays. So binary search trees and AVL trees are great compared to arrays, and linked lists because they're both they are both fast and at accessing a node, and fast when it comes to deleting or inserting a node with no shifts in memory needed. So binary trees such as binary search trees and AVL trees are great compared to arrays and linked lists because they are both fast at accessing a node and fast when it comes to deleting or inserting a node with no shifts in memory needed. Okay, that is magical to me because I know about linked lists and arrays and how the insertions are done. But if you know truly this is what binary search can do, then I'm impressed. So uh, we will take a closer look at how binary search trees and AVL trees work on the next two pages. But first, let's look at how binary search can be implemented, right? So we have, is there a code for this? Okay, good. This is good. This is good. So we have the binary search tree, which is these types of binary search tree. So there are different variants or types of binary trees worth discussing to get a better understanding of how binary trees can be structured. The different kinds of binary trees are also worth mentioning, right? Now, as these words and concepts will be used later in the tutorial, below are short explanation of the different types of binary. Did I post this in the description? Let me have a look. Okay, yes, I did. So here are some examples of or types of binary trees. We have a balanced tree. Yes, I read about this. So balanced trees has at most one difference between the left and right subtree heights. At most one difference. So does that mean we can't connect multiple trees, multiple nodes for one side more than the other? So let's say 18 has another node, right? We can't do that in a balanced binary tree. Okay, that's cool. That's cool. So let's see the next one. This is a complete and balanced one. So complete and balanced one. So it just has one level more than the other nodes. So complete means what does it mean? Binary tree has all levels of nodes except the last level, which is uh which can also be full, right? Or filled from left to right. The properties of a complete binary tree means it's also balanced. And we have a full binary tree, a perfect binary tree. The full one is a kind of tree where each node has either 0 or 2 nodes. I thought that was a complete node. Sorry, a balanced node. A full binary tree. Okay. A binary one has a balanced one deals with the heights. Okay. So a perfect binary tree has all leaf nodes on the same level. Let's see a perfect one. Okay. Okay, that's good. Right. So binary tree implementation. Here is an implementation of the binary tree. The tree above can be implemented much like we implemented a singly linked list, except that instead of linking each node to the next node, we create a structure where each node can be linked to both its left and right. Can be linked to both its left and right. So let's see, here's an implementation, which is what I already done. So we have the tree node is a good name. Okay. I'm not really good at naming variables, but let's see. Tree node is fine. This a function that runs when we create an instance of this tree node class. So then we do this, we set our okay, what will now be the value of the node? I'll just go because data is being set as a string here. So anyway, here's a node we have. This node here will have a left and right. This is our root node, by the way. So then we'll have other node that follows that same node. So I want to take a look at an implementation of the nodes of the binary search. Oh, what is the relationship between B and node E? The relationship between node B and node E. B is the parent of E, right? So E is the left child node, right? Left child node. Let's see, left. F is B's right child node. So where do you submit? Okay, yeah. This is not what I am looking for. I want I want an implementation of the binary trees. Binary trees implementation. Hmm. That's interesting. So we have a node class and then a print tree function that prints the nodes in the current node class. Well, I'm not sure about this, but let's see. So, inserting into a tree. To insert into a tree, we use the same node class created above, and add an insert class to it. The insert class compares the value of the node of to the parent node and decide to add it to the left or right node. Finally, print tree is used to print the tree. So we have a function that inserts a value into the node. So here is the insertion part, and this is what I'm really interested in. So we have the data. If the cell the data is null, then we stop. We don't insert. But when it's not null, so we say if our current data is less than the data we are trying to insert into. So it's the data you really compare in this case, right? That's interesting. Uh, Let me see. Were they doing the same thing here? Mm-mm-mm. Save. Trees are scary. Ah. Mm-mm-mm. So if there's a data in in this tree currently, then the new data we are trying to add. I mean, this is not really necessary. I just want to see this for myself. Just start. You know what? Let's do something here. I'll create a. I just want to have an implementation of a binary tree or a tree at in general. So let's say this is self what should I call this? So this will be binary, or let's call this, yeah, bin tree, right? Oh, sorry. Let me create a new class called bin tree. This bin tree here is going to be like this. So we'll create a I'll do this similar to the way I create linked lists. So binary trees will have a function, an init function, and so when we instantiate the binary tree class, we can begin to use every method or function within that class. So say self, I'll call this the root, self dot root, should be none at first. So insert, I'll call this insert node. So insert a node into our tree, and then we can do this. So we want the value of the node, value like this. Okay, so this is the function. Now before we insert a node into our linked list or our binary tree, right, we want to ensure two things. We want to first of all know if the tree is actually empty, right, or if there's no tree at all in this case. So meaning the root is none, right, which is what they are doing here, right? Let's say, let's come back here. Mm-mm-mm. Trees, trees, trees. Let's climb some trees. I'm not sure why they are using a deck here. There might be a reason to this, but hmm. Give me a second. Sorry. Today is really exhausting, honestly. Um, da, da, da. So. Do. Let's see, let's see. Why, why is this being added to the deck, to a deck? I don't get it. That's why I want to see a lot of implementations. So insert, right? So insertion, if self dot data. I don't like manipulating stuff directly, right? Or at least assign it to a variable. What you want to do. If self dot data is the data in the node class here. So if self dot data is there, so if the current node is not empty, is that what you're saying? And the data here, what? Hold on. How to implement a binary tree? Let's take a look at other implementation. Exactly. I mean, binary tree. This is good. So I have a feeling this guy will do it right. Um. So it needs node data. Okay. So I mean, why is the root not none at first? Right. I don't think this part here I agree with it. But let's see what's here. So in this example, we define the classes, two classes, a binary tree and node class. Node represents a single node. Okay. The binary tree class represents the entire binary tree and has one attribute, which is root. The root attribute points to the root node of the tree. We initialize the binary tree class by passing in the value of the root node. So to add nodes to a binary tree, we define a method called insert in the binary tree class. Here's an implementation. So, uh, hmm, 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 hmm. So insert is here. We have the node. If self dot root is none, okay. If the root is none, then we set this to root. This is exactly the same as the one um in linked list. This part here is exactly the same as linked list. So you set the, you can see there's a queue being used here as well. That's interesting. So if the queue, the current queue, we should pop this will remove the top, the first item in the array. If current queue, remove the left as well. So here we take this current node, right? The current node will be the first node, and then if it has a left node, right? If left is none, then current node dot left should be the new node that we want to insert. Okay. Hmm. So else q dot append current left. Current left. Current node dot left. Okay, so if there are no more, oh, okay. And q dot left. Okay, let's see. In this implementation, we first create a new node. I'm actually curious about this part, right? Here we are adding the nodes. Otherwise, if there is already a root, then we do this. But why? Append q to append current node, right? Let's see what I have here. So first of all, we need to verify it. The reason why I set this to none, right? I don't want to set it to any value, because if you set a value to the, okay, let me call it binary tree. If you set a value here, it means whenever you are creating an instance of the binary tree class, you must pass it a value, right? But me, I want to be able to create a tree without any roots. Technically, that's not good, but we're still, it's good to try out some things, right? So now, to insert, I'll say this is going to be the new node new node is going to be the node class, right? And then the node class requires a parameter, which is the value. It requires an argument, sorry, which is the value here. And yeah, so if we say if self, if not self dot root, which means if the root is none, then we add the current node as the root node. So self dot root should be equal to the current the new node we just created, new node, and then we return. Now this return here will prevent any other code from running. So yeah, here's how we create the root node. Now we want to be able to add more nodes in our linked list, right? So for us to do that, we can, let's have a look here again. I see they are using an array here. In this case, they are using the queue. Where is it? What was it? Geeks for Greeks. Yeah, so here they are using the queue. We are appending the queue, the root to the queue, right? We have a temp and a key node, which is something I don't really get, but do level order traversal to find deepest node temp and node to be deleted. The deepest node is the node with the longest, what do you call those stuff? Branches, right? Is it branches? Edges. Okay. Mm, mm, mm. Dun. I'm not doing 2 hours today. Certainly not. Can't do 2 hours today. Nah. My time is even up. I'm supposed to finish in an hour. I wasn't checking, but you know, binary tree simplified after the stream. I think this. Okay, let's see. Do level traversal, level order traversal to find the deepest node, which is temp, and the node to be deleted, which is the key node. Okay. Here, I think I read something similar here. Okay, in this first implementation, we create a new node object with the value of the data we want to insert, right? We then check if the binary tree is empty. If it is, we set the new node as the root of the tree. If the binary tree is not empty, we perform a breadth first search to find the first empty spot in the tree and insert the new node there. Oh, okay, I see what it's doing here. So here is an example. We create the tree like this, and then when we set a value, we will make a breadth first search. Let me copy this. Let me add this link to the resources. I would edit here so you can have access to this. If the binary tree is not empty, we can perform a breadth first search to find the first empty spot, right? And insert the node there. So let's see how the breadth first search is done. So we have a queue current node dot pop. If current node dot left is none, right, then we insert it to that node. Oh, okay. We insert our current node as the left of the current node. Hmm. Otherwise, if this node is not none yet, then we move to the right node. So breadth first search, we are searching across, right? Oh, okay. This makes sense now. If current dot right is none, current dot right should be the node. So where we find the empty spot, right, is where we insert the value. So here we are simply self the root here. I'm not sure what this is doing. I don't know why. Okay, so let's see. We are popping from the front, right? So the first one we'll pop is the root node. Oh, okay. So we pop the root node, but when we append q dot the right should be this. The q dot append is current node dot right. But does this modify the actual tree? I know q is this array here, blah blah blah. But at this point, right? Um, if we are popping a value from the array, right? Mm, so this will pop the first queue. Okay. Uh, you know what? Let me do this. I'll say if the queue is not empty. The reason why they use queue here is to just use this pop. I think pop left. Yeah. So where's this? Temp is yes pop left. So this is the current node, right, that we are looking at. The key node here will be what? Key node is equal to temp. So this also makes sense because temporary node temp here will help us store the topmost node, which will start from the root level, right? So let's say in the first situation, this will get the root node. Now, if temp.data is equal to key, what is key? Key is the value we want to insert. Oh, we are deleting here. Where's the insertion? Ah, okay, so this is insertion. So they are using a deck append roots, right? So if the temporary node has, so this temporary node will be the first node in the tree, or the roots if we start from the highest level, right? We'll get the tree, and then if temp dot left is none, temp dot left is going to be the new node. So basically, wherever we find the first empty spot, right? But I'm also curious, what does this root look like, right? What does it look like? If I used, let me see what happens when I do this. Dun, dun, dun. So let's say, let me create a node, right? Hold on. So I'll create a node binary tree, insert, um, let me see. Oh, I have some charts here. Let's refresh this. Oh, that's good. Keep studying. Keep studying. Um, somebody say How much? I think I do coding every day, so there's no really a quantified amount of time. It's just part of my daily work. So queues keep all nodes at current, right? Okay. Cancel this. At current level, that's the idea. Yeah. So I later got that. So the queue helps us keep the current node. Okay. The current node we are traversing through. All right. So where we start from the topmost node, the queue will help us keep track of those nodes. Yeah. 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 Not 247. Not 247. Yeah. Dun, 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 dun. Does code? I'm not sure. Does code life? Have you implemented? Have you used trees before? Have you used the trees algorithm before? Have you implemented a binary tree somewhere sometime before? Anyways, so wow, if the current root, if it's none, then we can insert this. I think the idea of inserting, creating an instance of the tree with a value immediately is because, right? Is because here I'll just put the value here. Sorry, it's because you can't have a tree without a node, right? I'm not sure if the node of the tree can be empty. Well, let's see. I can put the value here like this. So this will create an instance of the binary tree. And I want to see what this looks like. So let's say I do this. I say um, Q is, um, let's implement a deck. This is a deck. We import this deck class from the collections. Right? Okay. And then let me pass in this. So I'll say my tree is equal to binary tree. Let me see one. What will happen here? So this, you know what? Binary tree. You know, don't worry, don't worry. Insert. Um, I'll do it inside the function and wait. Does the value insert root 10? The root and 10. What's the session? Insert. Mm, mm, mm. This function is not even. So the root, if the root is there, return the root. Else use a deck. Checking, checking. Dun, 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 dun. I might have to end this stream and continue my studies. I need to understand this thing before tomorrow's stream. I need to understand trees before tomorrow. Ah, all right, guys. At least if you stayed from the beginning to the end, you'll probably be studying along. Otherwise, you were probably listening to me. But anyways, um, it's good. It's good. No, I'm not. I'm not a student. I'm not a student. I'm actually um a software developer. I build mostly. I code in JavaScript most of the times. Um, yeah. So JavaScript, React, Node.js. I recently started mobile development for a project I'm working on. I had no choice but to actually start developing the mobile app. So yeah. So I'm doing data structures and algorithm for the sake of understanding data structures and algorithms. Basically, I've been seeing a lot of people talk about it. It's really, the concept is nice, but like I don't like it when I can study something and I'm not doing it. So I just got curious and started doing it. And hopefully sometime by the end of this year I should become very good at it. Yeah. Not very good, but like decent. Yeah. Okay guys, so that's the end of today. You probably didn't learn anything from me today, but I'm sure if you were watching throughout, you would have seen me struggle, going from one side to the other to actually learn this concept. So one one source of one resource to learn something is not enough. So you have to scramble around, play around with things and see how they work, not just on the surface level, but like, dive deep and understand what is going on behind. Anyways, take care. I'll see you guys tomorrow. Bye.